Section 5.2, we're going to be continuing our discussion of the natural logarithm, but we're going to be taking a look at the natural logarithmic function in terms of integration. And what I mean is not that we're going to take an antiderivative or an integral of the natural log. What we're actually going to be doing is we're going to be taking the antiderivative of what gave us the natural log to start with. And we talked about this last time. So when we looked at the derivative of the natural log, we said that if we have a function natural log of x, then its derivative is 1 over x. That's what we said. So if we sort of take the antiderivative now of this, right, we will get back to where we started. So the antiderivative of 1 over x is the natural log of the absolute value of x. We're just going backwards. Okay, so before we took the derivative of the natural log, it became 1 over x. Now we're taking the antiderivative of 1 over x and it's becoming natural log. And it does become the natural log of the absolute value of x. So this is the going backwards. This is the antiderivative part. We will do an antiderivative gateway. It's not happening until we get about halfway through the class. But because we're going to be doing a whole lot more antiderivatives in chapter 8, that's why it shows up there. But when we get there, we will have to remember on that gateway and everything else that these absolute values keep coming back into play. So they only come into play for antiderivatives. So we're going to find the indefinite integral, or the antiderivative, of the integral of 5 over x. So 5 is a constant multiplier. What's the antiderivative of the over x part? Okay, so it's the natural log, and it's the absolute value of x. And then plus c. Yes. Thank you. Okay, is everybody good with that? Fine. Okay, let's try another one. This has a form that's going to have a log in it. Okay, but it's not as straightforward as the last one. Why not? Yeah, there's something of a chain rule going on. At least that's how we think of it in terms of derivatives, right? We have more than just x in the denominator. Now, when we think of chain rules backwards, do you remember what we did to do that? You have limited tools right now, very limited tools. Happened at the end of chapter 4 if you're thinking about your Calc 1 course, and if you took it here. Yeah, so if we're trying to go backwards, right, we're trying to take something that looks like it was a chain rule, and instead of taking a derivative of it, we want to take an antiderivative of it, we want to go backwards. What is the process that we have for doing that? U substitution. That's the only thing we have. I mean, that is the only tool you have now. Trust me, you're going to get a lot more tools in chapter 8, and you're going to wish you didn't. Okay, but right now, the good news is that it's only U substitution that you have to work with, so it must be U substitution. And the way that works is that we're going to let the denominator be U. So then, what is du? Remember, that means derivative of u. -3, and then dx. Okay? So in our question that we're originally given, this piece gets replaced by u. But the dx piece here at the end needs to be replaced by what dx is equal to. Well, this equation is not solved for dx, it's solved for du. But if I divide by if I divide by -3, which is multiplying by -1/3, I will have a replacement. So I'm going to jot that down very concretely on this first one. This is -1/3 du. So when I come back to my problem, the dx gets replaced by -1/3, typically we write it at the beginning, and du at the end. Okay? But once it's in this form, it looks just like what we want to do when we're going with our logs, right? This will become what? Well, the -1/3 will stay. That's fine. What happens for the antiderivative of 1 over u? Natural log of the absolute value of u plus c. But The last step in a u substitution is always to put it back in terms of the variable in which we began the problem, which it began. So instead of it actually being left as the natural log of absolute value of u, the absolute value of u will become the absolute value of 4 minus 3x plus c. And those absolute values are necessary because that expression 4 minus 3x is not necessarily going to be a positive number. Okay? All right, everybody good? Okay, let's take it a little bit step further. So this one looks really messy. And it might even look like, I don't even know if u substitution will work on this one. And it might not in some cases, especially when we do get to chapter 8. There's going to be other tools that you have. But the only thing you have to try right now is u substitution. And the u is going to be where you have the bigger power. And it's also going to be the denominator, which they coincide. And that's going to be on purpose, right? So the denominator is going to be my u. That's x cubed minus 3x squared. What then is the derivative of x cubed minus 3x squared? 3x squared minus 6x dx, right? Okay, now in this problem, I can replace this u on the bottom. I don't have just a 1 on top, or like I had over here. It was just a 1 on top, right? That's very clean, very simple, very straightforward. I have other things with variables in it on top. So in order for this to work, they actually have to get replaced somehow with the du part of what I just did. Now, it's not exactly the same thing. The numerator, it says x squared minus 2x, but my du part says 3x squared minus 6x. How can I change it so that they do match? We can take out the 3, right? So we can take it out or we can divide by it if you think of it that way too. So I can factor out a 3. And then I can actually do what I did on the previous problem. I can divide by 3, which is the same as multiplying by 1/3, and the 1/3 will be in front. What will then happen is that all of this will get replaced with the 1/3 in the front and the du at the end. The top ends up just being a 1. Yes?
So once you factor out 3, it's supposed to be x squared minus 2x?
Sorry, typo. Yes, in all the places. My goodness. Thank you, David. How about that? Better? I think it's better. I think it's right now. Thank you so much. Yep. Okay, what's our antiderivative? Well, the 1/3 comes along for the ride. It's the antiderivative of 1 over u. Natural log of absolute value of u plus c. Thanks so much. Plus c. And then the last step will be to do what? Yep, plug the u back in. So our u that we established was x cubed minus 3x squared. And my plus c. Again, those absolute values are necessary here. That expression is not always positive. The x cubed has the ability to be negative even if the x squared doesn't. Okay, the next one has a caveat to that. We're building, right? It's like a crescendo. Okay, so when we looked at the last problem, I made a comment and I said, we want our u substitution to be where we have the higher exponent. And I also said we want our u substitution to be the denominator, right? And I made the comment that it was both in this case and that was by design. This one didn't have that feature, right? The higher degree is actually on top, isn't it? We can't use logs. This isn't going to work if a higher degree is on top and we let the u be on top. I will never get a du that will work. So when we have a problem like this, we do have one other tool. It's not a tool that we've used in calculus so far, but you did use it back in a college algebra or an algebra 2 course. You probably didn't like it there, but you're going to be okay with it because you guys have developed mathematically since then. It's called long division. Ooh. Okay. So here's what we do. we take the numerator and we divide it, put it under a division sign, or as my son would say, it's under the house. It's under the house. And the part that's the denominator is on the outside of the house. Right? The division is by x minus 2, and we are dividing 2x squared plus 7x minus 3. Okay, so when we do long division with numbers or with polynomials like this, what we do is we ask ourselves this basic question. What do I have to multiply something by to get something else? In particular, for this one, we're looking at the x and the 2x squared. What do I need to multiply x by to get 2x squared? 2x. Yep. So I'm going to put the 2x here, and then I'm going to multiply the 2x on top by the x minus 2 on front. So the first piece is going to match identically. That's why we chose it. Okay, it has to. That's the whole point. The next piece doesn't have to match identically. So 2x times negative 2 would be negative 4x. Everyone good so far? What happens in long division next is that you subtract that value you just got from the piece above it. So subtraction here means changing both signs. So these two add to 0 when I change both signs. But 7x plus 4x becomes 11x. Now we're not done, and the reason we're not done is because our value in front, x minus 2, can still go into 11x plus or minus 3. It's still small enough to do that. So we ask ourselves the same question again. What do I have to multiply x by to get 11x? It's 11. So we're going to put plus 11 up here. 11 times x is 11x. 11 times negative 2 is negative 22. And then as before, we subtract, i.e. change our signs. The 11x's add to 0. What is negative 3 plus 22? It is 19, right? You get 19? All right. So we're done now, by the way. And the reason I know I'm done is because x minus 2 can't go into 19. One way to sort of think about that is that the exponents are smaller. Like this is an exponent of 1. This one doesn't have an exponent, meaning it has an exponent of 0. It can't go in any further. This is how I know I'm done. So when we get to the end of the long division work, the question is, what do we have? Well, we have this quotient that came out on top. So I'm going to rewrite this. This quotient that came out on top is 2x plus 11. And the remainder is still divided by the piece that we couldn't divide it by, right? X minus 2. And we've changed this expression now into something that we can do an antiderivative for. Because the denominator now has the bigger exponent, which is what we were saying we needed. I'll be able to do u substitution with it. It won't be very exciting. The exciting part is already done, okay? Now, the piece at the beginning, what is the antiderivative of 2x? It's x squared, or you could say 2x squared over 2. Yeah, it's x squared. What's the antiderivative of 11? 11x. Good. Hold tight, I'm going to give you something in just a second. And then what do we get for the derivative of 19 over x minus 2? Well, if we let the u substitution be x minus 2, what's du here? It's 1, right? So I'm going to give myself a little bit more space, but it's 1 and then dx. So it's a very quick, easy u substitution. I'll write it in just for the benefit of us seeing it. So this is going to give me still 19 on top, but now it'll be u on the bottom and du. Okay, so notice I shifted the notation for antiderivatives because I didn't do the last one yet, but I did do the first two. So I don't want the integral in front of the first two. I already did that. So this is x squared, this is 11x, and then I've got 19 plus 19, and the antiderivative of the over u part is, this is our new one, natural log, yes, natural log absolute value of u plus c Am I done? I need to plug my u back in. Yes. So x squared plus 11x plus 19. That 19 is being multiplied by the natural log of the absolute value of x minus 2 plus my c. Okay, the other part of this section we're going to take a look at is trigonometric integrals. Okay, trigonometric integrals. I'm sorry, we have one more before that. It was just so small in there, I didn't notice it. Let's try this one. Okay, one more time. Indefinite integral, and so we're taking a look at the natural log of x squared over x. I think it's probably worth pointing out the first thing is you can't bring that 2 down in front. Okay, some of you said yes, you got that. Why not? It's not squaring the x. You're exactly right, David. The x is not what's squared, right? The whole natural log is being squared, not just the x inside. So there's no bringing it down. Second thing to point out, I gave you an antiderivative sheet. I don't have a copy of one, but I'm pretty sure this is true. Do you see anywhere on there an antiderivative for the natural log of x? No. So, when something shows up in an antiderivative that you can't take the antiderivative for, because there's no property that you have learned, well, it must be that that's you. You do not have choice. Agreed? Yeah, it's got to be you, because I got to get rid of it somehow to continue in the problem. So then, what is the derivative of u? 1 over x dx. Now, this is written in such a way that it's not real clear, but I think you probably all see it. But in case you don't, let me remind you. This is the natural log of x being squared, and I have a 1 over x because the x is the denominator. Yeah? So this piece right here is the same as this piece right here, and it will be replaced with du. The natural log of x right here, grief. My pen's to work. The natural log of x right here is the same thing as right here, so it will be replaced with the u. So now I just have the antiderivative of the natural log of u squared. Okay, what's the antiderivative of u squared? U to the third over 3. Perfect. Plus c, yes. And then the last step is to replace the u with what it's equal to, which is the natural log of x. So you can either write it like this over 3, or you could write it like this if you prefer, with the 1/3 in front, 1/3 the natural log of x cubed plus c. Okay, trig. Some of these you've seen before. Well, two of them you've seen before. Back in chapter 4, we actually take a look at these two right here. The antiderivative of sine is negative cosine, and the antiderivative of cosine is sine. And yes, they all have plus c's on them. I got that, but more or less, right? Okay, the next 4 are new. We haven't done them or seen them before. So, the antiderivative of tangent is negative natural log of cosine of x plus c. The antiderivative of cotangent is natural log of sine of x. The antiderivative of secant is the natural log of secant x plus tangent x. And the natural log of cosecant of x is negative natural log of the absolute value of cosecant x plus cotangent x. Okay? These are all on the antiderivative sheet I gave you. Okay, so feel free to flip them over and copy it down here, because sometimes that's faster than looking at the screen and going back down to it. These are our trig integrals, the new ones especially, that show up in this section. So we're going to find some antiderivatives now that involve some trig. In particular, some trigs that we haven't done before. So secant. Secant's one we haven't done before. Now, if this just said secant x, it would look exactly like that other page. But it doesn't just say secant x, it says secant of x over 2. So it's not a very exciting u substitution, but there is a u substitution. And if you'll remember, another one of the sort of red flags for u substitution is that there's sort of this embedded parentheses where there's a function inside of something else. This x over 2 is inside of the secant. Okay? So there is a u substitution here. Eventually, and it won't be too much longer, you're not going to need to write this before you do this. You're just going to be able to move forward without even thinking about it as a u substitution. But we're probably not there yet, so we're going to write it down. So if u is x over 2, what is the derivative of u? 1/2. That's supposed to be dx. 1/2 dx. Now I need to replace dx, so I'm going to move the 1/2, and I move it by multiplying by 2. Okay, so I've got a 2 du now that will be replacing the dx. So the 2 will be coming at the beginning, the du will go at the end, and this will say secant of u. And then it's a direct application of the previous one that we just did, right, where we had the secant of x. It's the second one to the bottom on the paper. The 2 stays at the beginning. This is the natural log of the absolute value of the secant of u plus the tangent of u plus c. That's what it says. But we're going to put the u's back in. So now I have 2 natural log secant of x over 2 plus tangent of x over 2 and then plus c. Okay, so that's a simple u substitution one. It's not so bad. Now, one of the things that we did, we haven't encountered it yet because we're just starting the trig part of it, back in chapter 4, is we did look at some things with identities. If you would like, I don't think I have printouts of those, but if you would like a copy of an identity sheet, like from trig, the things that we'll be using most in this class, you're welcome to print it off. It is posted in Canvas. It has basic trig properties like the Pythagorean identities, the reciprocal identities, the quotient identities, things that you probably remember, but it also may have some other ones that you don't remember as well. It might have some things on there. We won't see them used until we get to chapter 8, but like double angle identities, right? Half angle identities, power reducing formulas, things like that. There's some of those in there too. So when we take a look at this one, it's tempting to look at this and say, is there some way I can do some trig simplification? And their answer is no on this one. The reason that the answer is no is because there's addition in the denominator. If the addition weren't in the denominator, I had just had cosine over sine. I could change it with a quotient identity. It would change into cotangent, and then I'd be back to the little, the list of 6 that I gave you before. But that's not what happened here. There's addition in the denominator. So again, the only tool you have, we do have the trig that we just identified as not being helpful. We do have long division, also not helpful. So the other one that we have is u substitution. So the u substitution is going to be the part that's in the denominator, right? That's our default because we're supposed to be getting logs quite frequently. To be perfectly honest, we're in a section that's titled logarithmic antiderivatives, right? The word log's in there. So we're going to let our denominator be u. I am not a fan of using t's. If you want to turn your t's into x's, it's okay with me. WebAssign's not going to be okay with that, so make sure you use whatever variable it gives you. But I'm going to use t on my screen, but I make it kind of curved on the bottom. Hopefully it won't look like my addition. What is the derivative of 1 plus sine of t? It's cosine of t, which is actually very nice, right? Because that's what's on top. So this piece right here looks exactly like this piece over here. So when I do my u substitution and do the replacement for it, my du is going on the end, or dt, because, no, du, sorry, I said it right, is going on the end. And then I have 1 over, and then it's u in the middle. What is the antiderivative of 1 over u? Natural log, absolute value of u, right? Plus c. But what's u? 1 plus sine of t. Now, you're welcome to leave this here, but this one doesn't need the absolute values. So you remember from a trig class somewhere along the way what sine graphs look like? They bounce up and down, right? Between what low value? -1 up to 1. So if I took a graph that's going from -1 up to 1, and then I added 1 to it, what's it going to do? It's going to shift the entire graph up 1, right? I'm not going to be negative. So on this particular one, if you see somebody do something like this, again, you don't have to do it, but if you see like the back of a book or you see WebAssign giving you an answer like this, they're not wrong, because this one actually is only positives or 0, right? The absolute values don't help in that case anyway, but it's only positive numbers anyway. So you could eliminate the absolute values on this one and be correct. In general, you can't. When in doubt, leave them. I just want you to be aware if you see them do that, you know why. All right, last one. This is a definite integral. Do you remember what definite integral means? What's the difference? Yeah, there's a step at the end that involves some subtraction. The part at the beginning that tells you that's going to happen is it has limits of integration, right? It has these up here. That's what makes it a definite integral. It has a starting and a stopping place. And we're going to do the subtraction on the end with it, just like Andrew mentioned. So taking a look at this one, I see something that has a log in it. That's got to be part of what in the world's going on with my u. I also see a naturally occurring parenthesis, like I can actually see it this time, which also identifies that my u is going to be the part that's in parentheses, 1 plus the natural log of x. So then, what is du? One over x dx, right? So this piece here at the end, sorry, good grief. This piece here at the end gets replaced by the du. I'm going to leave the limits of integration off for the moment. I've got my du at the end. The 1 plus natural log of x will get replaced by u, and it will still be squared. The reason I'm leaving off the 1 and the e is because I no longer have the variable x, and the 1 and the e apply to the variable x, and I've changed it to the variable u. Once we put the u's back in as x's, we'll put the numbers back in, okay? What's the antiderivative of u squared? U cubed over 3. I do not need a plus c. Why? Because I'm going to be substituting things in, it would cancel itself out, right? I'm going to do that subtraction step at the end. If you put the plus c's, it's fine. It's just going to cancel itself out. I do need to evaluate this then, though, at u is equal to 1 plus the natural log of x. So now I have 1 plus the natural log of x cubed over 3. And now I'm going to evaluate at the values, given e and 1. So I'm going to put the e in first. So 1 plus the natural log of e cubed over 3 minus 1 plus the natural log of 1 cubed over 3. So let's see if you remember, because we did these last time. These are a couple properties. What is the natural log of e? It is 1. So this is the number 1. What is the natural log of 1? It is 0. Okay, so if you have values that can simplify, you do. If this said natural log of 3, we'd leave it natural log of 3. That doesn't have a closed value that we have. It's irrational. But on this one, now I have 1 plus 1 is 2. 2 cubed would be 8. So I have 8/3 at the beginning. I have 1 plus 0 is 1. 1 cubed is 1 over 3, so minus 1 over 3. And 8/3 minus 1/3 is 7/3. And this can also be seen in your calculator. It's the same place that we saw. There's a couple places. Math 9 instead of Math 8. It's function integration. And inside of the graph, there is one below it. One below number 6 is number 7. One that looks like a script It looks like I can't do my S's backwards. A script S, this one, yeah, script S. And you can also do it on the screen as long as it's within the view of the screen. Okay, if you want to explore a couple of those options, I'm happy to do that, but I'll end right here so that we're not going any further over time. So, both lessons now have been completed, right? All right.